Okay, so talking about topics 3.11 and 3.12 in this particular segment of notes on spectroscopy and the electromagnetic spectrum and the photoelectric effect. Now, spectroscopy will touch on a little bit more detail, being a measurable lab technique where they're measuring absorption or emission. We'll go over like measuring tools of how to use spectroscopy in the lab in the next section where we talk about Beer's law, because we'll actually be applying it to that particular data gathering. But we're going to go background information on the electromagnetic spectrum and the photoelectric effect, and a lot of this is going to be review of Honors Chem 1 with a few new added little extras in the mix. Going over the learning targets and enduring understanding. Spectroscopy can determine the structure and concentration in a mixture of a chemical species. So as I said, that's the part where we're using the lab technique and then doing calculations from there in order to get the overall concentration or determine the structure of the species. First learning target, explaining the relationship between a region of the electromagnetic spectrum and the types of molecular or electronic transitions associated with the regions. So one particular region, we'll talk about microwave radiation, and it's associated with transitions in molecular rotational levels, rotation of molecules. Infrared radiation associated with molecular vibrational levels, vibrational changes in the molecules. And then, of course, this is the main one from Chem 1, ultraviolet visible radiation associated with electronic transitions, like jumping energy levels, jumping out, falling back, giving off visible light or ultraviolet light. You're going to be able to explain the photoelectric effect and then calculate wavelength, frequency, and energy of a photon emitted in an electronic transition in an atom or molecule. That also would apply to being able to calculate the energy needed to eject an electron, which would be part of the photoelectric effect. So those kind of calculations can be applied also there. So the first thing we need to review is electromagnetic radiation. So it's a form of energy that exhibits wave-like behavior. Electromagnetic radiation, of course, the photons travel in waves, but remember that electromagnetic radiation, even though we call it waves, it has photons or particle ability as well. So a stream of these particles that travel in waves. All types of energy will travel at the speed of light in a vacuum. And three primary characteristics of electromagnetic radiation is the wavelength and frequency are inversely related, and they equal the speed of light, using our relationship here where the speed of light equals the wavelength times the frequency. Speed of light is 3 times 10 to the 8th meters per second. That's a given constant value. Frequency for this equation is measured in hertz, which is 1/seconds. And then, of course, the wavelength for this particular equation is measured in meters. So that means anytime you're given a wavelength, when it's not in meters, you have to convert it to meters before you can do that. Now, looking at this diagram over here where it's showing you the different wavelengths, wavelength 1, wavelength 2, and wavelength 3, as you can see as you go down the diagram, the wavelengths are getting shorter. But what's happening to the frequency here, as you can see, as the wavelengths are getting shorter, the oscillations per second, of course, cycles per second is increasing. So shorter wavelength means higher frequency. That's why they're inversely related. So if the wavelength goes down, the frequency goes up. Inverse relationship. So don't forget that part, very important to know that particular relationship. The electromagnetic spectrum, reviewing different tidbits on the electromagnetic spectrum, the shortest wavelengths are gamma rays. They have the highest energy and the highest frequencies. And there, as you can see, this part related to the diagram. So that's why we have higher energy, higher frequency, shorter wavelength. So energy and frequency are pretty much direct there, and the wavelength is going to be inverse of both. So a higher energy means a shorter wavelength as well as a higher frequency. The next one in the line would be X-rays. Obviously these two are ionizing type energy that can really do a lot of damage and penetrate cells and organic tissue, and that's why they're cancer causing. Ultraviolet, also exposed to enough of that, can cause skin cancer. You know, it's also a little bit shorter wavelength, higher energy than the visible spectrum, called ultraviolet because it is just on the side of the violet waves. Violet waves are around 400 nanometers. Here's where you see nanometers, which is not meters, so you'd have to convert it. And if you don't remember, 1 times 10 to the 9th nanometers equals 1 meter. That would be the conversion factor to use there. Nanometers obviously are very small. Visible light spectrums, though, all measured in nanometers, so you want to be using that particular conversion factor. And then, of course, the longer side of the visible light spectrum would be red, which goes over here into the 700 to 800 nanometer range. And then on the other side of red is infrared, which later on we'll address infrared radiation and the vibrational levels for molecules. And then in between radio and infrared, this is where microwaves would fall, even though it's not particularly on this diagram, but that's where it would fall. And we'll be looking at microwave radiation has enough energy to cause rotational effects in molecules when it absorbs microwave radiation. Of course, radio waves are the longest ones with the lowest frequency, so lower energy, lower frequency, longer wavelengths over here on this side of the electromagnetic spectrum. Now, calculations and wanting to be able to use our formulas. So, for instance, they could give you a wavelength. Brilliant red colors seen in fireworks are due to the emission of light with wavelengths around 650 nanometers when strontium salts are heated. And I'm sure you recall the flame test lab when we lit the salts and you could see the pretty colors. So strontium would give like the orangey red color. And talking about fireworks. But we could calculate the frequency of the red light with this type of wavelength using our C equals lambda V equation. Now remember, lambda is the symbol for wavelength. That is a Greek letter. It's the lowercase version of the Greek letter lambda, but that symbol always represents wavelength. So here, though, before I begin, because this is in nanometers, I would need to convert that over. Hold on, let me fix that. That's just meters. We need nanometers here, so I'm going to go ahead and convert this over to meters before I plug it in. So 1 times 10 to the 9th nanometers equals 1 meter. When I do that calculation, then I get 6.50 times 10 to the minus 7 meters. So before you can plug it in, make sure that you change any kind of measurement in terms of wavelength over to meters. Because the speed of light, if you remember from the previous slide, it said it was 3 times 10 to the 8th meters per second. So we need that unit to match there. And we're looking for frequency. So now that we have our other values, we can go ahead and calculate. So 3 times 10 to the 8th meters per second equals 6.5 times 10 to the negative 7 meters times our frequency V. And then all it is a simple division, and the meters will cancel, and then you're going to be left with 1 over second over here. So V equals, let's go ahead and do that calculation. So punching in a few numbers too, looking up here for significant figures, this is our measured value in our problem, so it has 3. I'm going to keep 3 in my answer. So I end up getting 4.62 times 10 to the 14. Now you can write it in hertz, because hertz is the same thing as 1 over seconds. So either way, that would be correct in showing your calculation. So make sure on these that you write out the formula, show the substitution, and then you get your answer. Also show you any conversions you need to do in order to change it over to put it into the formula. And look, there we go, correct answer. Now looking at this particular example, very similar to the one that we just did, because we're going to calculate frequency again. But in this case, we're looking at the wavelength of a green light from a traffic signal centered at 5.2 times 10 to the minus 5 centimeters. So this one's in centimeters rather than in nanometers. So really the only thing different here is making sure that you convert it over to meters before you begin. So 5.2 times 10 to the minus 5 centimeters. And if you recall your conversion factors for centimeters to meters, there would be 100 centimeters in 1 meter. So when you divide this out, you get 5.2 times 10 to the minus 7 meters, because centimeters cancel. So now that we have that, we can now plug into our equation the speed of light equals the wavelength times the frequency equation to get our correct answer. So plugging in the value for the speed of light, which does not change, it's a constant value. Plugging in our wavelength times 10 to the minus 7 meters, and then times our frequency. And then we can calculate and get our final answer. So once again, rounding to 3 significant figures, since our measured value up here has 3 significant figures. This is going to end up being 5.77 times 10 to the 14th. Once again, the meters will cancel, so I'm left with 1/seconds or hertz as my final answer for the frequency here. Now, Max Planck, he was part of the development of the quantum mechanical model and all of the science of the beginning of the 1900s, and basically came up with the idea that matter could absorb or emit any quantity of energy. He sort of disputed that fact, that it could absorb and emit any amount. So what he proposed, based on all of his observations and data collection and experiments, that matter can only gain or lose in small, specific, or discrete, they like to use that word, discrete amount, and those small packets of energy or discrete amounts of energies he called a quantum. Like an individual one would be a quantum, but plural, if there's multiple packets of energy, multiple discrete amounts, that they would be called quanta. And they like to use the staircase analogy for this, because you can't go halfway up a stair, so it's kind of an all or nothing deal. You have, where the continuous, you have the little spaces in between as you're going up the linear, deal. So if you're going up a linear deal, yes, you have every single amount of energy. But to go up a step, it's all or nothing. You can't go halfway up a step. So you would have to, in order to get to that next level, completely absorb the entire amount of energy, enough energy to get you to the next step. So the staircase analogy is kind of the idea of like each step is a quanta of energy. Now, this was later, the formula of calculating energy came from this idea where you have energy equals Planck's constant times frequency, which Planck's constant is 6.626 times 10 to the minus 34, and this is joules times seconds, if you can see that over there. Now, you don't have to memorize Planck's constant. It's on the formula sheet, so you would have that value, so you don't have to worry about memorizing that one. So is the speed of light, by the way. You don't have to memorize that one either. So here, using the energy equals Planck's constant times frequency, now we can not only know the wavelength and frequency, we can now calculate the amount of energy involved with different amounts of electromagnetic radiation, different photons. So let's look at an example where we might want to use this. Blue color in fireworks is often achieved by heating copper 1 chloride to about 1200 degrees Celsius, pretty hot. Blue emits light having a wavelength of 450 nanometers. Okay, so 450 nanometers, what is the increment of energy or quantum that is emitted? So when that one particular electron gets emitted and you see the blue light, okay, want to know how much energy is involved with that's being released when you see the blue light in the fireworks. So there's one of two ways that you can do this because they gave us the wavelength. So you could use your speed of light equation and figure out the frequency like we did in the previous problems. And then you can plug in your frequency into the E equals HV equation, plug in your frequency that you calculate, and then you can end up getting your energy. Now, if you're pretty good with substituting, you can combine these two to make it all go in one particular equation because they both have frequency in them. So that means you can move the variables around, like you can make this C over lambda equals V. All I did was divide lambda on both sides and move it over here. And same thing over here. I could make the V equal the E divided by H just by moving the H over to the other side. Now that these are both set equal to V, or frequency, they can equal each other, like so. Okay, and then if I wanted to solve for energy, all I would have to do is multiply both sides by H and stick that over on the other side. So C times H over lambda equals energy. And you would get this particular equation if you decided to combine the two. And if you do it this way, then you don't have to do two separate calculations. You can combine them all at once. But if that, your brain doesn't follow that, stick to plugging in this equation first, find your frequency, take your frequency and plug it into this equation and find your energy. So you can still do it that way. I mean, this is more of the more efficient way of doing it, so that's how I'm going to do it. But once again, I still need to have my wavelength in meters before I can begin. So 450 nanometers, 1 times 10 to the 9th nanometers equals 1 meter. And you'll find that it's 4.50 times 10 to the minus 7 meters. So get that converted over first. Then you can plug everything in. So we get speed of light times 10 to the 8th meters per second times Planck's constant, which is 6.626 times 10 to the minus 34 joules times seconds over the wavelength, 4.5 times 10 to the minus 7 meters. Now meters will cancel, the seconds will cancel, and then we are just left with our joules, which is what we want anyways. So getting that joules here, after multiplying these two together on the top, dividing by the bottom, we end up getting 4.42 times 10 to the minus 19 joules. So for every electron transition that occurs, it's going to be 4.42 times 10 to the minus 19 joules. As you can imagine, it's a very small amount, but that's the discrete amount of energy needed to produce that blue light. And that's what the firework color is doing that. So for each electron giving off a blue light photon, it's going to take 4.42 times 10 to the minus 19 joules for that to occur. And of course, obviously in the sky, if you're doing the fireworks, there's going to be many electrons, transitioning in order to produce all that color. So there would be multiple photons being given off when you look up into the sky for fireworks. So that'd be multiple packets or multiple quantized energy coming off of each one of those electrons. All right, here, this one's a little bit different because it wants you to find the wavelength in nanometers of a photon that has a frequency of 6.165 times 10 to the 8th megahertz. I don't know if you remember the megahertz conversion, but mega, like meter equal, to megameters, or like megabyte, you remember that one. But mega is, 1,000 times greater than a kilo, like a kilometer. So this would be 1 times 10 to the 6th meters equals 1 megameter. So same thing, it would be 1 times 10 to the 6th hertz is going to equal 1 megahertz. The megahertz is a typical measurement, used in frequency. So we would need to convert that over first. And we have to find energy and wavelength, so we do really need to use the equations separated here because we have to do both. So I wouldn't want to combine them for this particular problem because I'm finding both the energy and the wavelength. So I'll go ahead and convert over my frequency here. This is megahertz. Do your T-chart, diagonal down your megahertz, which is 1, and then 1 times 10 to the 6 hertz here that goes on the top, then the megahertz will cancel, and you get 6.165 times 10 to the 14th hertz. So now that we have our converted frequency, because remember to use this equation here, it's meters per second, the wavelength's in meters, and this would be like 1 over seconds for the hertz, because hertz equals 1 over seconds. So you couldn't just plug in the megahertz here, it would be incorrect. But now that I have that, I can plug into my equation. I have the speed of light, 3 times 10 to the 8th meters per second. That's going to equal the wavelength times the frequency here. And in this case, dividing by the hertz, 1 over seconds, so these would cancel. And I'll be left with the wavelength in meters, and then I can convert that over to nanometers. So 3 to the times 10 to the 8th divided by our frequency. If I can type it in correctly, apparently I added one more 6. And we will be able to get your wavelength. So here I'm getting the wavelength is 4.866 times 10 to the -7 meters. Now I went to 4 significant digits because this measured value in our problem has 4 significant digits. Now I can easily convert this over to nanometers because that's what it said it wanted. So 1 meter equals 1 times 10 to the 9th nanometers, and do that conversion, and I should get 486.6 meters. So that's one part of the problem done. So I got the wavelength out of the way. Now I can do the energy over here. E equals hv. I don't know the energy. I do know Planck's constant, 6.626 times 10 to the -34. Once again, you're not responsible for memorizing that because it's on your formula sheet, so you should be able to just look it up. Times our frequency here, 6.165 times 10 to the 14th hertz, which is 1 over seconds, which you'll notice here the seconds will cancel and you're left with joules. When you multiply those two together, 6.626 10 to the -34 times our frequency, it's going to be 4.083, no, sorry, 5, this should be a 5, if I did that correct, times 10 to the -19 joules. Hopefully I calculated that correct. Let's see. Yes, and apparently I forgot to leave on the 5 here in the answer, but yes, it should also have 4 significant figures, and you would keep that in there. So 4.8 or 4.085 times 10 to the -19 joules. All right, let's talk about the photoelectric effect. Einstein is, really the one that observed this and decided to run with it. And he used Planck's idea of the quantized energy to explain it. That his assumption of quantized energy, the emission or ejection of electrons from the surface of a metal, is in response to light being shined on it, that incident light. Now this was the interesting observations, light below a certain threshold frequency, meaning a certain wavelength, because the frequency and the wavelengths are inversely related. No matter how intense that frequency was, though, it did not cause the electrons to be emitted. So lower energy, longer wavelengths didn't eject the electrons. However, light above the certain threshold frequency, where it did have shorter wavelengths and higher energy, even if it wasn't very intense, the electrons did they were ejected from the metal surface. So this application here, E equals HV, only photons with enough energy will eject electrons. That's going to hold true, so you can calculate the amount of energy needed to eject a certain electron, with a certain wavelength or frequency. You can figure out that energy needed. There's also a video here, a little video showing the photoelectric effect if you'd like to watch it. So this is kind of the example question that I saw about using and applying these equations to the photoelectric effect. Because here they gave us a photoelectron spectra of magnesium. And I don't know if you remember these, but this is where you could apply this concept in here. This is what's on the formula sheet, so I put them in here so you could see the different ones that they give you. They give you both the formulas and they define all of the different constants here for you to use. So this particular example says calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of magnesium shown in the complete photoelectron spectra over here, I guess above. So really we need to decipher and look at our spectra here to figure out which would be the ones in the valence. Now if you remember your photoelectron spectra, here is our energy, megajoules per mole. Now looking at our spikes here, you want to look for the side that has more energy. So this would be the 1s. That means this is the 2s. That means this is the 2p. And this would be the 3s. So the outermost electron shell for magnesium would be this one right here, would be the valence one. And it's telling me it's 0.74 megajoules per mole. That's what I know. And this is per mole of electrons, by the way, because we're talking about ejecting electrons, okay? So here, calculation-wise, I just want the radiation needed to remove one electron, not moles of electrons, an electron, so I need to get to that idea of just one electron, and I can, figure out the wavelength of what that would appear to be. So I have to do a conversion here because I have 0.74 megajoules per 1 mole of electrons. Well, I need only one electron. So either one you can convert first, it doesn't really matter. And if I want to figure out wavelength, I'm going to eventually need my equation here of, the E equals CH over lambda, and I can figure out the lambda here. That's where I combined both of these two together to make it easier. So I can figure out the energy. I know the speed of light, I know Planck's constant, and then I can determine the wavelength from there. But in order to get there, I need my energy to be in joules, because it's in joules in this equation. And then I need my moles of electrons to be just 1 electron. So I need the joules per 1 electron. So I'm going to get rid of the electrons first. So in order to get rid of the mole of electrons, I need to diagonal up that. So 1 mole of electrons equals 6.022 times 10 to the 23rd moles, no, sorry, electrons, because we're talking about the particles here. So this is going to be the particles. So in 1 mole of electrons, there's 6.022 times 10 to the 23rd electrons, just using the value off of the formula sheet here provided. Avogadro's number. Remember, Avogadro's number is the number of particles in any mole of anything. Okay, so I convert that over, so the moles will cancel good, and I'm getting it per electron. Now I got to get rid of megajoules and change that to joules. I'm going to put megajoules down here, and put joules up here, and 1 times 10 to the 6 joules equals 1 megajoule, using that conversion factor. Now I can calculate the joules per electron, and I can use that in my equation below. So 0.74 times 1 to the 6th divided by Avogadro's number. When I do this, I end up getting, let's see here, the megajoules will cancel, end up with joules, so this would be 1.2 times 10 to the minus 18 joules. And now that I have that value, I can plug it in down here. So 1.2 times 10 to the minus 18 joules equals the speed of light. And I guess technically I should use their number off of the formula sheet here, which is 2.998. So I'll go ahead and just use their number. They provided on the formula sheet, 2.998, although it's very similar. Meters per second times Planck's constant, 6.626 times 10 to the minus 34 joules times seconds, and then divide it by lambda, which is what I want. Do your calculations, basically cross those. The lambda comes up, the 1.2 times 10 to the minus 18 goes on the bottom, and you can calculate your wavelength. So doing those calculations, I get my wavelength, which looks like it's 1.7 times 10 to the minus 7 meters. And then that would be my answer, because I'm looking for the wavelength here. So this is a kind of an application question, application example, using the formulas, applying it to a photoelectron spectra, and also being able to do the math conversion of the megajoules per mole of electrons into joules, actually, and technically this would be joules per electron, by the way. So this would be, you know, the meters for that particular electron. Now it's much prettier here on this particular setup here. As you can see, the T-chart, same thing. Megajoules cancel with megajoules, moles cancel with moles. You end up with joules per electron here. And then you plug it all in, and I isolated it to lambda over here, and you can get your wavelength. And once again, going back over spectra, 1s is the one with the largest energy. The one with the lowest energy would be your valence, which in this case for magnesium is going to be 3s. Now the line emission spectrum, because we're about to talk about electronic transitions, was studied for various elements in this time frame when they're developing the quantum mechanical model. Once looking at these line emission spectrums, especially Bohr looked at hydrogen in detail and did lots of calculations with hydrogen. But you see that only discrete wavelengths were observed. There were 4 particular color wavelengths, lines that appeared on the spectra for hydrogen. So let's talk about what those lines mean in the visible spectrum, because it's caused by electronic transitions. So if we're looking at just the continuous spectrum, it would just be a rainbow of light. But here, if we're actually putting it through an element in the gaseous tube, and looking at through the slits, it breaks up into these four bands, these four colors. Everything else would be black in the spectrum. Now I put neon on here also to show you the different one. Neon has many more electrons. Hydrogen's simple because it only has one electron. But neon has 10 electrons, and as you can see, it has a lot larger spectrum with different lines. And remember, the line emission spectrums are like fingerprints for the elements. Each element's going to have its own particular set of electronic transitions with discrete amount of energy that are going to produce certain wavelengths. And that's why we get these different ones for each element. And it can be kind of like considered a fingerprint of the element. So that brings us to the idea of electronic transitions. And we use the Bohr model a lot of times to visualize this, even though we know the Bohr model is not correct. We know there's those different shaped orbitals and all of that other stuff, and not really rings around the nucleus. But let's try to imagine the process of an electronic transition. You know, the ground state, it's at its lowest energy level possible. So like 1s2, the electron's there in the lowest one and being in that 1s orbital. But if it absorbs energy, it can jump to a higher energy level. And that's when it gets into this excited state here. Going to the highest energy level, it's going to absorb that necessary amount of energy in order to jump to whichever level it's jumping to. If it jumps to 2, it's not going to be as much energy as if it's jumping to, say, 4 or 6. Ones that are farther distance, although the energy amounts for each packet or each quantized amount of energy is not the same because the distance between the orbitals are not exactly the same either. So it absorbs, it jumps out to a higher energy level. When it falls back to its original ground state, it drops back to the lower energy level. As it does, it will release the energy, and it's that same amount of energy that it absorbed. And because of that, so when it releases it, if it's on the visible spectrum, we can see it, and that's how we can tell the wavelength. But that same amount that was absorbed is now being released, and then it's given off in electromagnetic radiation, or a particular type of radiation that's on the electromagnetic spectrum. So we say light, a photon, it could be, a gamma ray, it could be an X-ray. If it's invisible light, then we would be able to see it. If it's ultraviolet light, we wouldn't be able to see it because it's not in our visible range. However, you can use other laboratory techniques to detect it in the UV spectrum. Now, the electronic transitions, this is a very good diagram to recall here. As you can see, like looking at this absorption, this electron's jumping out one energy level, a shorter distance than, say, this one over here, which is jumping out a couple energy levels. So as you can see, the wavelengths of the photon striking it are different. This one's a little bit wider in its wavelength, so that means it's lower in energy. This one's shorter in its wavelength, so that means the energy being absorbed by this electron obviously is higher. That's why it's jumping out to a higher, to farther distance away from that nucleus. Now the emission part is falling back to its original state, but it's giving off that same amount of energy. The wavelength here related to the energy and the frequency, of course. Same thing here, if it's falling back 2 energy levels, it's giving off that same amount of energy in the form of whatever radiation had originally struck the electron. And if I'm looking at this correctly, this one's showing maybe like a red photon, a red light photon striking it, and over here would be more like an orange light photon striking it, if we wanted to compare it to colors on the visible spectrum. But this is kind of the general idea of absorbing and emitting photons. Now, like I said, the ones we see are on the visible spectrum. The ones we can't see would be on the ultraviolet spectrum. And AP considers the electronic transitions to be occurring between ultraviolet and visible light. Now you'll see in some of the electronic transition diagrams that they also have the Paschen series, which is considered infrared, but that's where it gets a little murky. So for AP purposes, the only ones you want to consider being electronic transitions are in the UV spectra and in the visible light spectra. Infrared, we're going to consider that vibrational. and not in the electronic transition category. So here showing you the different electronic transitions. This is called the Balmer series for hydrogen. And it's showing you like the red one obviously isn't as far of a distance as the green one and the blue one or the purplish. And then the true violet one, which jumps the most energy levels. It goes from 6 down to 2. And that difference, of course, means that more energy was absorbed. It corresponds to that purple color over here on the line emission spectrum. Same amount of energy that was absorbed to get it out here to energy level 6 is being released as it's going the other direction. That energy is equivalent to the wavelength based off of our equations. And we could also figure out that frequency if we wanted to. So energy of a photon depends on the difference in the energy levels. And really, it's not really a distance, okay? It's really an amount of energy between the energy levels. But because it's easy to visualize looking at the rings on the Bohr model, you could think about it as in terms of visually like it's a distance, but it's really packets of energy. So this diagram shows you the different electronic transitions for hydrogen. So we have the Lyman series, which is a part of the ultraviolet, and then the Balmer series, which is really mostly considered visible light. The Paschen series is infrared, but like I said, that's where it gets a little murky in terms of like, are these true electronic transitions or not? But here you can see the differences in the energy. This is a difference of 10.2 electron volts. Okay. So if I wanted to go from ground state energy level 1 to energy level 2 here for hydrogen, if I'm absorbing energy going away from ground state, they would have to absorb 10.2 electron volts. Now if I was going the other direction, emitting it this direction, going back to ground state, then it would be negative 10.2 electron volts because it would be being released. So energy leaving the system or being released is always given the negative sign. Energy being absorbed is always going to be given the positive sign because it's going into the system. But as you can see here, these electronic transitions aren't as huge differences in energy, so that's why they fall in the visible light spectrum, whereas these ones over here have a much greater measure for the Lyman series, and that's why their energy differences are going to fall in the UV ultraviolet spectrum. Now you can play around with the electronic transition SPET simulation here. There's a link if you want to. There's lots of different tools in there that you can mess with and look at different patterns in order to give off different colors or even ultraviolet radiation. Now let's talk about the other transitions besides the electronic ones. So kind of the review of Chem 1 is now over. These are kind of new ideas here, other transitions. The first one being microwave radiation. So if you're looking here, microwaves, like I said before, are in between radio waves and infrared in terms of size. So they don't really have a lot of energy. They're kind of longer wavelengths. But when microwave radiation hits certain molecules, it ends up causing them to rotate. So if certain molecules absorb microwave radiation, they're going to spin, basically. I'm going to show you an example by using the PhET simulation down here of what that looks like. So this is less energy involved in this particular kind of situation with microwave radiation. The infrared radiation is associated with vibrational changes, and that's this where you see the stretching and the bouncing and the bending. Okay, so here's the diagram. You'll see it in the simulation in just a second what it really looks like, but where it vibrates and stretches and bends, whereas rotational, they actually spin. Okay, so looking at that, these are different, ways that they appear. So the vibrational ones are going to require more energy because they're in the infrared section. That's when you absorb infrared radiation will cause the vibrational transitions. And so it's more energy than rotational, but it's not as high of energy as visible light or ultraviolet, where we're talking about electronic transitions in this particular area. All right, so let's take a look at that PhET simulation, and I can show you a few examples. Okay, so pulling up the PhET simulation here is what you can see. You can select different types of light, like I can select microwave, infrared, visible light, ultraviolet. So of course, if I zap this with ultraviolet, nothing's happening for that particular molecule. And you can see that the molecule I have up right now is carbon monoxide. But let's see what happens if I hit it with some microwave. Nothing. Oh, no, there it's spinning. Okay. See, it's absorbing, and then you see it actually, after it spins, it releases the energy. So that one, as you can see, the microwave's causing rotations in the carbon monoxide. Let's look at infrared and see if this one responds to infrared. It's not all of, yeah, as you can see, the stretching, but as it's absorbing, it does the vibrational and then it ejects it. So not all molecules are going to have the same type of absorption pattern either. So keep that in mind. Like we could look at nitrogen here, see if that one works for infrared. Nothing's happening for infrared here apparently. So the nitrogen molecule wouldn't be absorbing and releasing infrared. But I guess if we try ultraviolet, let's see what happens there. Nothing. Okay, so certain molecules, let's take a look at water, and you can play around with the simulation. Not all of them are going to absorb. Let's look at the infrared for water. Definitely is absorbing and vibrating. Let's look at if it does rotational. As you can see, it definitely absorbs the microwaves and rotates. So if you want to, you can check out all of these different molecules over here and see which ones respond to which types of radiation. You can look at the light spectrum diagram here to take a look at the electromagnetic radiation. So it's right here fresh in front of you. You could go slow motion if you'd like, but you can play around with this simulation, but it's pretty basic. Microwave, if it absorbs the radiation for microwaves, it will rotate. If it absorbs the radiation for infrared, it's going to vibrate. So that's the basic points that we're looking for there. So let's look at a type of example free response problem they could ask you. And it may not seem obvious at first, but hopefully you'll catch on. Example 6 here, iodine is a purple gas and nitrogen is a clear gas. So I don't know if you know that an iodine crystals, when it sublimes, it gives off this pretty purple gas. So explain the following statement about these gases in terms of atomic structure. Well, nitrogen molecules absorb ultraviolet light, but not visible light. Iodine molecules absorb both visible light and ultraviolet light. Well, if I think about this, the visible spectrum is what I can see, and those would be all of the colors on the visible spectrum. So if iodine's purple gas, that means I must be seeing purple photons coming off of it. In order to, purple photons, if I'm seeing a purple gas, I must be seeing purple photons coming off of that particular gas. Nitrogen's clear though, so I'm not seeing anything, so that's not on the visible spectrum. So basically what I would say here is that the iodine shows the purple because of the visible spectrum that it's absorbing. So it's obviously absorbing enough energy that would give off purple photons that we would see in the purple gas. And then, of course, the nitrogen, which only absorbs ultraviolet, is going to be out of our spectrum of viewing, so we wouldn't be able to see that one, but it would absorb the ultraviolet light. So response here, ultraviolet light possesses more energy than visible light, so there must be some lower energy electronic transitions available in iodine molecules. that are not present in our nitrogen. And that's why we're seeing the purple color gas that shows those purple photons in the visible spectrum. So the lower energy electronic transitions are occurring in iodine, whereas they're not occurring with nitrogen. They're only occurring in the higher energy electronic transitions in the ultraviolet range, not visible to us in the visible spectrum. Another type question is they could give you a diagram showing you different absorptions for different molecules. Like here's nitrogen, here's carbon dioxide, here's water, here's oxygen and ozone. And you're looking at ultraviolet, visible, infrared on here, short wave radiation versus long wave. And these blue spikes here, you know, this is just regular solar radiation, so this would be like the sun. But here, the nitrogen, carbon, water, and the oxygen. So on here, we're looking at the blue sections, which are showing the different absorptions at different wavelengths. And that's how it kind of looks once you'll see in the, when we do the Beer's Law lab with the spectroscopy, it's going to show absorption with these spikes, and they're going to look like little hills on the graph at certain wavelengths. So these blue areas are showing where they're absorbing. And here it says like micrometers. But what you can see is here there's some absorption in the infrared, a little spike here right on this cusp of the visible radiation, but a lot of spikage, this blue section in the ultraviolet area for ozone and oxygen. Now you probably know from environmental science that ozone does absorb ultraviolet radiation. That's why it's really good to be up there in the stratosphere. But if you look at water vapor, though, it has no absorption in the ultraviolet section. Its absorption is occurring in the infrared section alone over here. We're not seeing any spikes in the visible light area either. Carbon dioxide is even lower in the infrared, and then nitrogen is also in the infrared here. So based on the graph to the right, which molecules show electronic transitions occurring? So for electronic transitions, you know, I said AP defines that as UV or visible light. So that's the sections you want to look for those that are having electronic transitions. Infrared, of course, that section would be for vibrational. So if I'm looking here, the only one that's going to produce electronic transitions, that's going to be your oxygen and ozone. The oxygen and ozone show absorptivity in the visible and the UV section. So visible here, UV, which means that we have electronic transitions occurring. Water, carbon dioxide, nitrogen, although this isn't part of the response, just want to note that they're all over here in this infrared section. That's where they're showing spikes in their absorption, absorptivity, of course, and that means they're only exhibiting vibrational transitions, not electronic transitions.